Okay, so last time was mainly finding the expression for the electrical power in steady state. So steady state means this transient voltage, EF or EQ, it doesn't change, it's constant, and there's a constant angle between it and the terminal generator voltage. And in that configuration, we were able to define the electrical power of the synchronous generator. And that followed a relatively simple expression. This first term is both for the round rotor and the salient pole generator, and it's just the product of the voltages divided by the reactance times the sine of the angle between them, between the voltages. And then for the salient pole generator, there's this additional opposing reluctance power term to account for the saliency. So that's this attraction in order to minimize the reluctance path. The equivalent generator circuit was two circuits, one for the q-axis and one for the d-axis. And in the d-axis, there was a EMF because it's only in the rotor axis, this induced force or voltage. And it's called EQ because the voltage lags the d-axis by, or the voltage lags the magnetomotive force by 90 degrees. And then if you had more sort of reactances, you could just put that into this equation and just make sure to use the voltage at the very end. From this more complicated model, or this total model, you can see that this voltage is not just one EQ, but there's EQ dash and even ED dash and ED and EQ double dash. So this is because during transients, this single reactance, which we modeled, this XD and XQ, they change, or the effective reactance changes. And now will be some intuition about how that happens. So if we start off, we can look at the expression for reactance, and you can see that it depends on the number of windings and also on the reluctance. So the reluctance is this resistance to magnetic flow or flux. And so if the configuration of coils changes, then so does the reactance. And that lets us start with this analysis. So during transients, what basically happens is there is a sudden change in the current, typically a short circuit or something like that, in the current and voltage which the circuit sees. And due to the principle of conservation of energy, if there was a flux going through some circuit or some coil before, then there will be currents induced in the coil, depending on the reactance of the coil, in order to dampen out these changes. And to motivate this with a simple example, if you consider this very simple circuit here, where you have a voltage source and some resistance, and it's initially connected to some coil, and since there's a DC current going through the coil, there's a flux generated, and this flux just loops through this iron core. So this is like a one-sided transformer, and there's some leakage flux as well. What happens if you short circuit this? So if you kill the connection to the voltage source, and the analog in the power generation is that there's a three-phase short circuit on the generator terminal after the transformer. So you lose the grid voltage. Well, initially technically there's no voltage source anymore. This is just a wire, so there's no voltage, there's no current. However, because there was a flux here before, the principle of conservation of energy basically states that this flux can't sort of change instantaneously. So if there was no resistance in this coil at all in this wire, then the flux would remain constant. And since this current no longer comes from the voltage source, it has to be induced due to this flux. And so you would have a constant current induced here to maintain this flux. However, of course, due to some resistance, this current eventually decays, and the time constant here is given by L over R. And L is proportional to your reactance. So if you have a small reactance, you have a fast time constant, and if you have a big reactance, you have a slow time constant, and opposite for the resistance of the wire. So now we can go on to describing the windings, which are in the synchronous generator, which eventually will explain why we have a difference between the steady state case and the transient cases. So the windings we already know is that in the stator or armature, there are 3 phases, and each phase has its own inductance. And we typically just assume it's the same for all of these phases. Then in the rotor sides, you have your field winding, which is the only one we've been concerned with, and it's the only one which matters in steady states. And so you have a field winding, and it's driven by some field voltage or excitation voltage and some excitation currents. Now, however, to dampen out electromagnetic changes due to short circuits and stuff, these rotors are typically designed with a D-axis and a Q-axis damper winding. Usually the one on the D-axis is stronger. And these are just empty coils, which are not connected to anything. So we don't apply any DC current to them. There are just coils that are put on the rotor. And their only purpose is when, for example, a short circuit occurs, currents will be induced in these coils in order to dampen out this effect so that the flux is most as constant as possible. So you have this in the D-axis, and you also have this in the Q-axis. So if we now consider, this is basically the same. It's saying that if you get a short circuit, then you will get some current induced to maintain the voltage. Because the rotor is rotating, a DC current in the rotor is going to be a AC flux, and opposite an DC current in the stator is going to be a AC flux in the rotor. But that's not so important. The more important thing, I think, is if we consider the physics of what actually is the difference due to these windings. So if we now consider a 3-phase short circuit, immediately after the fault, there will of course be a flux going through the rotor, and suddenly this flux will be induced in the stator coils to sort of maintain a constant flux. Initially, these damper windings have not sort of acted yet. And so the damper windings, the currents which are induced there, they will force this flux out of the rotor so that the rotor flux remains most constant. And if we drew this as an equivalent circuit, then you would see your armature coil, you would see your field coil, and you would also see the damper windings. So your effective reactance would be pretty small because this is a parallel configuration of coils. So you would get a very small reactance. And this initial state where the damper windings dampen out, that's called the subtransient. Then once the damper currents decay, so once the currents that are in these damper windings decays, then the flux starts to enter the face of the rotor. So it enters through the damper windings. These damper windings are usually at the end of the rotor, and it enters through the main windings. But now currents are induced in the field windings, and these also push the flux out of the rotor so that the flux is maintained most as constant as possible through the rotor. And so since it's no longer affected by the damper windings, the effective circuit is only affected by the armature inductance and the field reactance, so these 2 reactances. And so they are also in a parallel configuration. So you get a effective reactance which is bigger than the subtransient case. And finally, once also the dampening field currents decay, all the flux goes through the rotor, and then the only inductance which is being seen is this armature inductance. And so you will get the D-axis synchronous reactance, which is the same as we looked at in the steady state case. So basically, depending on which coils are active in the dampening process, the fluxes see a different equivalent reactance. And you can call for each of these states, you can define a different induced voltage and a different reactance. And these are this E dash, E double dash, X dash, X double dash. The double dash corresponds to the subtransient case, and the dash to the transient case. There's a few nice sort of intuitions when you look at the scale of this reactance. Remember that the time constant of the decay of these dynamics is L over R, and if you write out with the reactance, that's just X over omega R, where R is the resistance of the coil. And what you can see here is that if you have a smaller reactance, your dynamics are faster. And that makes sense that your damper windings, which are very strong, they decay very fast, so you have a very small reactance. And your transients are a bit slower, and your steady state, of course, is steady state. Yeah. Furthermore, you can see that you only decay if there is a sort of resistance in this winding. And the damper windings are also built with a very high resistance. So this RD is very big. Often you can neglect the resistance in the field windings, at least during this initial state. And therefore also this time constant for the subtransient dynamics is actually very quick. It's just a few milliseconds. Whereas for the transient dynamics, it's usually a few seconds. Yeah, that's enough intuition about what these different things are. One can, of course, calculate these effective reactances by simply taking the parallel configuration of the different coils and everything. However, usually in the datasheet, they already provide the transient and the subtransient reactances. And just like in the steady state case, these exist both in the d-axis and the q-axis for the salient pole generator. For each of these, so in steady state, our sort of equivalent circuit was just one induced EMF behind some d-axis reactance, and then you have some q-axis reactance and some terminal voltage. For the subtransient and transient states, the induced voltage is due to these damper windings also having a q-axis component. It can actually also have a d-axis component, the voltage. Again, the voltage lags by 90 degrees, so what's on the q-axis as a force becomes on the d-axis as a voltage. And that's why if we drew the circuits for these cases, you would also have transient and subtransient EMFs behind their corresponding reactances. And that basically introduces all of the states which are in this advanced model. So now you sort of know what is E dash and what is E double dash. And they simply correspond to so the calculations are the exact same. The way you calculate this voltage and its angle based on the voltage and the current and the reactances. So you just sum up the JXI and add it to the terminal voltage to get it. But the different reactances, they correspond to which coils are active in that transient phase. And these time constants, they are just L over R or X over omega R. Okay, so what remains to understand is just some intuition about where these differential equations come from. And I won't go into the derivation. However, there was one differential equation in these basic electromagnetic formulas, and it was Faraday's law. And this is the differential equation, which in the end is going to give the differential equations we're interested in. So you can set up basically a voltage equality across the circuits, and then set that to the negative derivative of the flux. And the flux is just L times I. When you do that, so when you just set up the voltage circuits and you set up the mutual inductance and you start by applying Faraday's law, after some rearranging, you get a few formulas for the derivative of this transient EMF, and you can do the same for the subtransients, etc. And there are multiple sort of configurations of this, but the one that's usually added in the simplified models is this one. And you can see that the dynamics of the transient EMF, they depend on the field excitation. So on the excitation current in the field. And this EF is just the steady state, EQ. And they also depend on the rotor angle. So that's a very sort of hand-wavy explanation of where these differential equations come from. It's also worth mentioning, you can put all of these different transient and subtransient and steady state values into the same circuit diagram. And then you will get something like this. So for the Q-axis, there is this field voltage, which is not there in the D-axis. But then due to these subtransient and transient reactances, you will get some sort of D-axis transients and subtransient voltages. And there's a general sort of structure to these differential equations, and that's your derivative of your voltage. It depends on your voltage before it in the circuits and the voltage after it. So it's sort of the difference here between these. And then the current times whatever reactance is between them. So this is sort of the same structure. So the rate of change of this voltage is equal to the difference between these voltages plus the current times the reactance between them. And this is the same sort of equation applied to all of these. And what we can do now is also understand what's actually the difference between all of these models. And you can see that the difference is basically the 6th and 5th order model. They include this subtransient. The 4th and 3rd, they only include the transients. And the 2nd doesn't even model the change in the transients at all. There's a slide sort of, so even though you don't model what you're basically saying in the 4th and 3rd order models, and the second one is that your subtransient dynamics, they are so quick that you don't really care about the dynamics, you don't care about the differential equation. However, since these correspond to the damper windings, and the damper windings are most of the damping in the synchronous generator, you have to include this damping. And we'll get to that now shortly, but the way that's done is by adding this linear damping constant. So you can see for all the low order models here, it has this d times delta omega damping. And that's basically to account for the fact that we're no longer modeling the the subtransient EMFs. So we don't use those anymore in the calculation of the electrical power. And so we have to account for the damping of the damper windings through this d constant. The difference between the 6th and 5th and the 4th and 3rd order models, it's a bit subtle, but it's related to this d-axis transient voltage. And this d-axis transient voltage, you can remember the transient is related to the field windings, and the field windings are technically only in the d-axis, which means in the d-axis, you shouldn't even have this. So in they are only in the d-axis, and if the windings are only in the d-axis, then the voltage should only be in the q-axis. However, in round rotor synchronous generators, the core can get these dissipative currents called eddy currents, and these can be in the q-axis, and that's why you would get a d-axis transient. However, for the salient pole generators, the core is what is called laminated, and so these eddy currents don't occur. And that's why you only get the transient dynamics in the q-axis. So the transient voltage only exists in the q-axis, and so you don't model this this d-axis transient changes. And so that's the difference between the 3rd and 4th. Is here the d-axis transient is with, here it isn't, and the same here. For your subtransient, you have damper windings in both the d and the q-axis, and that's why both are always with. Also worth noting, again, that's salient pole generators. Those are the hydropower ones. So for hydropower, you would use the 5th or the 3rd order models. Okay. I said I would sort of get to this damping, and that's part of this next bit, which is now we have this model. How would we do a disturbance analysis? So small disturbances, then you can do a linear analysis. Large disturbances, you have to do some sort of nonlinear analysis. So those are the two sort of analysis cases we'll go through now. Starting with the linear analysis, as a recap, you had this block diagram, and there you had the swing equation driven by the power imbalance. Integrating gives the rotor angle, and then the rotor angle and your grid voltage or terminal voltage and your induced voltage, they form this electrical power. And just to recap that, if you look at the equation for the power again, you can see it's exactly a function of this field voltage or an internal voltage and the grid voltage, and this internal voltage, it had some dynamics associated with it, which were a function of the power angle as well, and that's why. And also in the power equation itself, the power angle comes, and that's why when we look at the this cloud, which is generating this electrical power, it's a function of the rotor angle, the terminal voltage, and the induced voltage. And so, as we just said, if you don't model the damper windings explicitly, if you, for example, consider the third order models, which is typical for hydropower plants, then you want this E to include also the damper winding effect. And so already we consider now damping power, the mechanical power, that's already included in this D. So the mechanical friction and stuff, but it's typically very small and can be neglected. There is also this this rotor flux dynamics. So this equation here, the dynamics of this transient EQ, they actually have some sort of damping effect. So it can be called a type of damping power. And in a linear setting, the way you would deal with that is by simply, you have your equation for your electrical power here, and it is a function of this EQ dash. So in the transient case, you of course use the transient values. And if you derive that or derivate that with respect to this EQ, then you get some linearization constant there as well. And again, you have the same for the just electrical power synchronizing constant, where you have just taken the derivative with respect to the power angle. So you can linearize this electrical power with respect to these two variables. And then this term in the top here, it can be viewed as some sort of damping as well. But the main damping is the damper windings. And here's a long derivation, but basically by using these subtransient reactances, so that you use the reactance in the d-axis, damper windings, etc., and you find some resistance equivalent, and then you know that your power is just your current square times your resistance. You end up with this chunk of an equation. But basically the damping power due to the damper windings is something which can be evaluated for a certain operating point, and it's proportional to your speed deviation. And so this can be just put into the D here. So this equation is what is this damping constant. It's not the mechanical or friction, it's due to the damper windings. And so this is the final linearized model of the synchronous generator. Your electrical power has been linearized with respect to your power angle, your internal transient voltage, because this one can change, and your damper winding effects have been put into the D constant. So that's the third order linear model. So knowing that, how would you do some analysis here? Just some graphical intuition first. The swing equation is driven by the power imbalance between the mechanical and the electrical power. The mechanical power can be viewed as fairly constant for the time frame in consideration. As a reference already, the frequency control part of the control of generators, it moves this mechanical power. So that's how it works. But more about that later, I guess. The electrical power is just the sine of this angle times some voltage product, as we've gone over multiple times. So if you have an equilibrium, that means the derivative is 0, and so your mechanical power equals your electrical power. So you can see that you have two sort of operating points here. And this one on the left side, you have a positive gradient of your power angle curve. So this one is stable, and the one on the right is unstable. And previously, we in the very start, I think we motivated that by just some control engineering analog. We said this feedback loop will be negative if this constant or if this gradient is positive, and it will be a positive feedback loop if this gradient is negative, and that's why you need to be in the positive gradient part to be stable. But also you can just do this from a intuition point, which is a bit useful. If you consider that you're on this side now, and you consider for some reason, for example, an increase in your mechanical power, what happens then is that you have more mechanical power than electrical power, and so your rotor will accelerate due to the swing equation, so you will move to the right. And you will move along the power angle curve, of course, and what you can see then is as you move to the right, your electrical power will approach your mechanical power. If, however, now we started on this side and the mechanical power increased, again, of course, the mechanical power increases. So we move in this direction. But if you move in this direction along the curve, you move actually away from the equilibrium point. So you will be unstable. And the transverse or the inverse is the case for if your mechanical power reduces, then if your mechanical power reduces, your electrical power is bigger than your mechanical power. And so you will decelerate, your rotor angle will move to the left. And if you start at this equilibrium and move to the left, then you move towards the new equilibrium. So you are stable. But if you start here and you move to the left, you move actually away from this equilibrium. So it's unstable because whatever happens, you move away from the equilibrium if you are on this side, and the opposite is the case if you are on this side. Which power angle characteristic are we looking at now in the transients? And that is basically this transient power angle characteristic, which is the exact same as the steady state one, except you use the transient voltages and the transient reactances. And the transient reactance, you get that in the data sheet. It's basically including the resistance and the extra coils of the field and the damper windings. And these transient voltages, you calculate them in the same way with the phasor diagrams by just multiplying by the current and finding the power angle and all of that. But just make sure you use the transient power angle characteristic for all of this. Okay, so we have established that we will use the transient power angle characteristic. And if you look closely, you can see that we have PEQ dash to indicate that we're now looking at the transient power characteristic. And now we will just, previously in this initial graphical explanation, I said we will move along this curve. But we didn't really talk about how the rotor angle actually swings here. And it can be useful to just look at that. And so consider now that we start at this point 1 and then something happens and we move to point 2 where the electrical power is suddenly bigger than the mechanical power. Since the electrical power is bigger than the mechanical power, you will now decelerate. So the rotor will, the rotor angle which is starting up here, it will decelerate. And as it decelerates due to the swing equation, it will accumulate some velocity, which means once it gets to the equilibrium, it will actually overshoot. And if you don't have any damping in the system, it will overshoot sort of to the exact same amount, and it will just swing back standing oscillations. But due to some damping, the overshoot is a bit smaller. Of course, the same goes for the overshoots. You're suddenly below your mechanical power, which means you will accelerate again. And then you will swing back. And so that's how your rotor sort of swings and dampens in towards its equilibrium after a disturbance. This DEQ, this damping. So this damping here, it's just a damping constant. It will dampen these oscillations. It's a bit interesting to look at how this DEQ changes if you actually model the rate of change. So if you model these flux dynamics as it's done in the advanced model here. So what happens if you actually model this this rate of change, this differential equation? Then the situation is similar to what we just discussed here, except you will no longer just move along the electric power curve. So I'm just putting in the top here the part of this transient EMF which depends on the power angle, and you can see it's out of phase with it. And what that basically means is, consider the same case. So you start in point 1 and you have a disturbance to point 2. Now your electrical power is bigger than your mechanical power, so your rotor will decelerate. And then as your rotor decelerates, your transient EMF, it will oppose, so it will be following this. And as it is reducing here, it will actually reduce the electrical power. And since it reduces the electrical power, the deceleration area here, it will be smaller than what it was before. And so your overshoot will be smaller. And at the same way, once you've reached down here and your mechanical power is bigger than your electrical power, your transient EMF here, it will oppose again, so it will be bigger. So it will actually increase your electrical power from where it was before, and so it will reduce the acceleration area. And this basically just dampens out the system more. So the effect of these rotor flux dynamics given in these the effect of these transient rotor flux dynamics, these equations, is basically to provide some additional damping by generating a induced voltage that is out of phase with the rotor angle. Also worth mentioning, the reason it's out of phase, if you look at the equation, is because these constants here are negative. Yeah, this A constants. There is a important. This is a slight teaser or spoiler for the reason why you have something called power system stabilizers. If you have a AVR, a automatic voltage regulator, eventually this constant can change sign. And then what happens is this damping is no longer out of phase, but it's actually in phase with the electrical power, and you will actually have negative damping. So you can go unstable. So that's just worth keeping an eye out, is that these rotor flux dynamics, usually they will stabilize, but if you have a very aggressive voltage controller, then they can actually end up producing negative damping. And that's why you can't make the voltage controller very aggressive, or else it will affect your rotor angle and your frequency stability. This was all sort of just a graphical analysis. If you want to do a proper linear analysis, you can just linearize the swing equation. And so if you include this rotor flux dynamics, then you will add the additional states. So you'll have 3 states, for example, in the third order model. But for now, we will just consider that we ignore this additional damping, and we just consider the standard equation where the damper windings are just given by this D constants, and your electrical power is just the synchronizing torque times your power angle. And this can, of course, this is already a linear equation. So you can find the eigenvalues of this, and they look like this. And then, or like this if you use the inertia constants. Of course, if you have eigenvalues, then you can, if they are oscillating, you can find the damping ratio and the frequency of oscillation from these eigenvalues. And you can see things that, for example, as your damping increases, your response becomes more damped. So your damping ratio here, your zeta or your alpha, they will increase, and similar argumentations for the amount of oscillations. Here is a summary of the linear models. So this is basically the third order linear model. So now we also include the effects on this EQ. This looks a bit complicated initially, but it's actually just what we've seen before. Down here you have the swing equation. This damper constant here, it takes into account the damper windings because we don't model the subtransient EMF separately here. This is just the swing equation. This K1, it's a function of this power angle. So this is your synchronizing constant. So you've taken your PE and you've taken the partial derivative with respect to the power angle. And that's this constant. This one is this D, E. So that's this linearization constant with respect to the transient EMF, which is up here. And if you model this derivative differential equation, this rotor flux dynamics, then if you remember, it was a function that was of the field voltage, but also of the power angle, and it was linear. And so you have the full third order linearized model here. And then, of course, you need the nonlinear model in order to find suitable values for these both the damper windings damping and also the synchronizing constants. This is, of course, still just one machine. I'll say a few very brief words about how you can do analysis if you have more machines or multiple machines, and that's pretty neat. It's called modal analysis. And very briefly, of course, for one system, you had a swing equation, and you could find the eigenvalues of the swing equation. And for each, for this set of eigenvalues, there's a corresponding damping and frequency of oscillations. If you have a real system with numerous generators, then you have many assortments of these models. And unfortunately, these models are all linked together. So they all affect each other and there are interrelations. And so you can't just say that there is one frequency associated with one frequency of oscillation and one damping associated with one generator and another associated with another generator. Sometimes these generators swing against each other and have some relations. And modal analysis is a technique to basically look at the oscillations or the dampings and so look at the disturbance characteristics of your total power system and be able to attribute that to the different generators. And you do that by basically, so you have maybe 30 generators, so you have 30 times maybe 3 if you use the third order model, differential equations. So you have 90 states for the system. And so there's a big matrix or system matrix for the linear system. And you can decompose that into the so-called eigenvalue decomposition. And basically what that tells you is it no longer looks at just the states separated in the generators, but it looks at the characteristic modes. So at least you know if you have 90 states in your system, then there will be 90 specific eigenvalues. And each eigenvalue, because in linear analysis, the response is just e to the minus lambda t, each eigenvalue of a system matrix is corresponds to a specific amount of oscillations and damping. Once you have these eigenvalues, then you can look at the so-called eigenvalue decomposition or the mode shapes, which is basically, it relates these states to these system modes. So you have your states, which is your generator 1 frequency, your generator 2 frequency, and these are a function of these 90 or so oscillating modes which are in the system. And just an example of how that would look for a simple system. If you have a power system with 2 areas, in the first area you have 2 generators, in the second you have a third generator, and of course here there are multiple sort of modes, characteristic modes in the system, but let's say that 2 of them look like this. So here you have one set of complex conjugate eigenvalues and another set of complex conjugate eigenvalues. And you can tell from the real value that this first set is not very damped. So it has a damping of just 3%. So it's these oscillations will remain in the system. And its frequency, by looking at the imaginary value, is around 0.5 hertz. The second one, it's more strongly damped, as you can tell from the real value. It has a damping of 10%. And also it has a higher frequency because it has a higher imaginary value here of the eigenvalue. It has a frequency of 1.5 hertz. So, but these are sort of general system modes. So how do they correspond to the individual generators? What you can do is you can look at the mode shapes, and the mode shapes are basically the coefficients in this relating the state to these modes. So the modes are called Z, and you can call the states X, and between them there is a matrix of so-called mode shapes, which are just coefficients in this matrix. So each state is a weighted sum of these specific system modes or characteristic oscillatory modes. And if you plot these, so just to show how such a matrix would look, for example, this is just a part of the matrix, then you can see your 3 generators are made up of different combinations of these 2 modes. One thing that's worth noting, for example, just from this matrix, is that your mode L, so your higher frequency, very damped mode, it has very small coefficients for generators 2 and 3, which means this mode is not that present for those generators as it is for generator 1. While the K mode, so the one with the 0.5 hertz and low damping, it's present in all 3 generators. And if you plot these complex number, these coefficients, you get these mode shape plots. And these mode shape plots, you can get these for real big power systems, which is pretty cool because then every generator, you can see how much of each mode is present in that generator. And so here you see basically what we saw from the matrix just now, that your mode L, it is mostly in generator 1. So this says omega 1, while your mode K, it's equally in all generators in the amplitude. However, you can notice also from the phase of these coefficients that generator 3 swings against generator 1 and 2 for this 0.5 hertz low damped mode. So if we sort of ground this to reality, how would this look after a disturbance, this power system? It looks something like this. So if we start with the mode which is present in all systems, you can see that there is this 0.5 hertz oscillation and all 3 generators. So green is generator 3, orange is generator 2, blue is generator 1. All 3 generators have this 0.5 hertz modes. You can see that generators 1 and 2, they swing out of phase with generator 3. And that corresponds to what these mode shapes told us. Furthermore, you can see that while generators 2 and 3 seem to only have this 0.5 hertz mode, there's this sort of high frequency or higher frequency mode present only in generator 1, but it disappears quite quickly. And that's because this high frequency, highly damped mode was mostly present in generator 1. So that's how these mode shapes are useful. And if you do this for a whole power system, for example, the entire Nordic power system, what you can say is, okay, we've been observing this oscillatory modes. There's some oscillations in the power system. Which generator is causing this? And then you can look at the mode shapes and maybe it looks something like this. And then you can tell, okay, this one generator in Finland is causing this oscillation. And that's where you should put your voltage regulator or your power system stabilizer, or you should do something with your governor. It can also tell you which areas swing against each other. So for example, maybe the southeast of Norway swings against the south of Finland, that they are always out of phase. And then you know sort of what will happen if one area falls out, you know the effect on the other area. So this is just a extension of these simple linear analysis techniques for systems if you have many generators in a power system. Some final words about large disturbance analysis. Then, of course, you remember for this simple linear diagram, these are just linearization constants. So they depend on an operating point. And if you, for example, consider your synchronizing constants, of course, the gradient of this curve changes a lot on operating points. So if you have a large disturbance, so technically this example here is a large disturbance because you can see clearly that the gradient of this curve here is very different from the gradient of the curve here. So in this case, you would have to use some nonlinear stability analysis. And I'll just briefly motivate one type of nonlinear stability analysis called the equal area criterion, and it's basically based on these acceleration deceleration areas. And so let's consider a short circuit. So here is our pre-fault circuit with our transient d-axis synchronous reactance, our transformer, our line, and our system reactance. So they're just an equivalent reactance. And then usually after the transformer, we model some type of short circuit. And then you can get an effective reactance by using some star delta configuration stuff. The most important thing there is that the worst type of fault you can get is a three-phase short circuit. And that basically means that your entire current just flows with zero impedance down to ground, and your grid voltage completely disappears. And if your grid voltage disappears, your electrical power goes to zero. And so if that happens, and because you should always use the worst case for example, stability margin analysis, then let's say we are chilling at our operating point and then the fault occurs and suddenly our electrical power goes to zero. What happens then? Our mechanical power is still constant here. We have no fast frequency control, which is adjusting that. So due to our swing equation, we will accelerate with the mechanical power. And so the rotor angle will start accelerating, and this is like a quadratic acceleration because it's a second order swing equation. Then at this point, we reconnect the system. So we finally get back our electrical power. And so immediately our electrical power will, because our rotor angle has already started drifting, our electrical power will already be bigger than our mechanical power. So it will try to dampen this. And you can intuitively tell the longer we wait with reconnecting, the bigger this acceleration area and the smaller this deceleration area. And if you wait too long and your deceleration area is not enough to dampen out or to break this rotor acceleration back again, then you will sort of accelerate here, but you have already gained some velocity, and here you're trying to decelerate it. So you can see the gradient here is reducing, but you don't have enough time. And once you've already passed this point, then you're on the wrong side because now your electrical power is lower than your mechanical power, so you'll just keep accelerating quadratically, and your generator will lose synchronism. So the equal area criterion is basically you are stable until this area equals this area, and then you are unstable. And what this, how useful this would be in like a real-time implementation is questionable. You can define some stability margins based on that. For example, this area 5 or 4, 5, 6, 7, which is sort of the area that would equal the acceleration area. So that's the area that's actually being used to decelerate. The ratio of that area to your sort of total available deceleration area, you can call that the transient stability margin. And you can also, I guess this one is the most operationally important, you can define the critical clearing time. And so from the equal area criterion, you can find the critical angle. So that's the maximum power angle where your areas are equal. And then using just the swing equation and the mechanical power, you can find the time taken for this quadratic acceleration to reach this angle. And then you know that you have to clear your fault within this time. I find this large disturbance analysis more useful just to understand the effects of different quantities on the stability of the system. So first of all, if you didn't have a three-phase fault, so if your electrical power didn't fall all the way to 0, but it was just on 1 phase or 2 phase, then your electrical power doesn't fall that much. And since your electrical power didn't fall all the way to 0, then your acceleration area is smaller. So you are in much more stable case. Your loading, so your mechanical power before the fault, it greatly affects stability. If you produce some low mechanical power, then of course, if you lose the electrical power, the power imbalance will be smaller. And so you will be more stable. You will have more deceleration area once you reconnect. Whereas if you operate close to your maximum operation, your acceleration area, if you should have a short circuit, will be massive. So you will be very unstable. Since your governor, your frequency control loop, changes your mechanical power by adjusting the valve gain, this is how this can help stabilize the system. So if you considered here this fault, if you have a fast frequency control loop, what it would do, it would realize, okay, we're starting to get a frequency error. We should adjust our mechanical power. So it would reduce this mechanical power and thereby both reduce the acceleration area and increase the deceleration area. So that's how frequency control and mechanical power can stabilize the system. And for me, it also makes some intuitive sense that you have to pay a price in stability when operating at higher mechanical power. So the more you produce close to your limits, the more sort of you have to pay instability margins. And finally, the topology and the fault location. So since your electrical power has reactance at the bottom, and your reactance is a function of where this fault occurs and sort of the properties of the transformer, for example, then obviously it will change the height of your electrical power curve. And if your electrical power curve changes its height, then also the acceleration and deceleration areas change. And so the topology also greatly affects this. Good. Going back to our advanced model, now we basically should have a intuition of where all these states come into play, where they're used, and also this large disturbance, small disturbance stuff. That's basically if you want to analyze based on simplified models. Of course, these models here are more simulation models. They are a bit harder to work with for analysis. So that's why you have the analysis and control design part, which you typically do with the linear models, and then you simulate it in this proper big power system. Yeah, the remainder now is basically just understanding the turbine governors, where they come from, and maybe some voltage control loops or PSS, power system stabilizers. And in the end, also the frequency control architecture, which is just setting the power set points to the different governors. But this basically concludes the modeling part of this course.